Dear students, welcome to SRK online classes. Today we are discussing about the stereoisomerism in 6 coordinated complexes. Yesterday also we discussed about stereoisomerism in 6 coordinated complexes. Difference is, yesterday I have given all monodentate ligands with the different combinations. Today we are discussing about bidentate ligands. 6 coordinated complexes with the bidentate ligands. Now first, what are bidentate ligands? First we'll discuss about the definition part of bidentate. Bi means what? Two. A ligand which is capable of donating 2 pairs of electrons is said to be the bidentate ligand. A ligand which is capable of donating only 1 pair of electrons is called as monodentate. If it is capable of donating 2 pairs of electrons, it is said to be the bidentate ligands. Today we are taking bidentate ligands. And bidentate ligands are broadly classified into 2 categories. Look at here. Bidentate ligands are classified into 2 types. One is symmetrical bidentical ligands. Second one is unsymmetrical bidentical ligands. What are symmetrical bidentical ligands? Here I have given. If donor atoms are same, both the donor atoms are identical, it is called a symmetrical bidentical ligand. Example I have given, ethylene diamine is an example of symmetrical bidentate ligand because here donor atom is nitrogen, another one is also nitrogen. Both the donor atoms are same, therefore it is called as symmetrical bidentate. And put it another way, this molecule can be divided into 2 equal halves. See, if I cut here CH2NH2 and CH3NH2, both the sides it is same. That's why it is said to be what? Symmetrical bidentate ligand. Now look at other side, unsymmetrical bidentate ligand. Bidentate means donates 2 pairs of electrons. But here unsymmetrical means donor atoms are different. Nitrogen is donor at one end, oxygen is donor at another end. In the previous case, both the donor atoms are nitrogen, therefore it is said to be symmetrical. Now donor atoms are different, therefore it is said to be unsymmetrical bidentical ligands. And symmetrical bidentical ligands are abbreviated as A and A. Both donor atoms are same. Unsymmetrical ligands are represented as A, B. Donor atoms are different. Now, the first combination I have given MAA3, a bidentate ligand. Similar type of bidentate ligands are 3. Right? That combination I have taken. M is the central metal, A is symmetrical bidentical ligand. Here I have given a specific example. M is the central atom that is called as a cobalt, and A symmetrical ligand ethylene diamine. 3 molecules are there. The last class we have discussed about geometrical and optical isomerism. In geometrical isomerism, you write the pairs of ligands. But remember, these are bidentical ligands. Say A and A, one ligand, A and A, another ligand, A and A, another ligand. Only 3 pairs are possible. I cannot write in a different way. Therefore, geometrical isomers for this combination is 0. It cannot show geometrical isomerism. That is the first important point. Now, look at this structural formula of bidentate ligands. Here I have a metal, 3 ligands are there. So 6 positions are occupied by 3 ligands. A and A, one bidentate ligand, A and A, another bidentate ligand, and A and A, another bidentate ligand. Now, if you look at carefully, it looks like an optically inactive compound because we can cut this molecule into 2 equal halves from this side. Means a molecule which is having plane of symmetry should to be optically inactive compound. It is looking like a plane of symmetry molecule, but originally this molecule is not having a plane of symmetry. I'll take one example here. Look at this one. Here I have taken a octahedral molecule. Right? These are the 4 corners. 1, 2, 3, 4. This is 5th one. This is 6th one. It's an octahedral molecule. Now look at here. A and A is connected. So I am taking, this is one end, this is another end. Next one, A and A is this way. So these are not in one plane. If I bisect, one will be above, another one will be below. I'll repeat once again. A and A, this is upper part. Now the second one, B and B is the lower part. If I bisect, One will be upper side, other one will be bottom side. It is not having a planar symmetry. But if I write in two-dimensional structure, it looks like it is having a plane of symmetry. Another proof for that one is, now I have given a mirror image. This is a mirror I have placed here. Its mirror image. Look at that one. A and A here. This is A and A. Second part A and A and this one. If I place this molecule over this one, they are not superimposable. I think everybody knows this is one-handed. If I place in front of a mirror, it has its mirror image. If these two are like this, superimposable. If these two are like this, non-superimposable. For example, this molecule I am taking, I am placing over this one. Look at carefully. Here, this A and A will be here and this will be other side. So they are mirror images but non-superimposed mirror images. We know that non-superimposed mirror images are said to be what? Optically active compounds. It is not having plane of symmetry, but it is having a non-superimposed mirror image. Therefore, it is optically active compound. So, geometrical isomers are zero, no geometrical isomers, but one optical isomerism is possible. One is D, other one is L. I cannot say which compound is D and which compound is L. I can say one of the compounds rotate plane polarized towards right side, another compound rotate towards left side. Therefore, they are optical isomers. So, with this combination, geometrical isomers are zero, but two optical isomers are possible. One is D and second one is L. I am taking the third example. Second example, sorry. AB taken thrice I have taken. See the difference. AA, symmetrical bidentate ligand. AB, unsymmetrical bidentate ligand I have taken. Unsymmetrical means two donor atoms will be different. Now I have represented the possibilities. I can write AA, AB and BB, one possibility. Second one, AB, AB, AB. Apart from this one, I cannot write third possible structure. Therefore, with this molecular formula, two geometrical isomers are possible. In the previous case, no geometrical isomerism. But here, how many geometrical isomers are possible? Two. One should be the cis, second one should be the trans compound. Look at the first one. I have given one ligand, one bidentate ligand AB, second bidentate ligand, third bidentate ligand I have. Why I have represented cis? Minimum two groups are adjacent. Look at here. A and A 90 degrees, B and B 90 degrees. Out of three combinations, two combinations are 90. Therefore, I have given it cis compound. Second compound I have taken. Keeping these two constant, I have changed these two. Then it becomes trans. Look at here. A and A opposite 180. B and B opposite 180. So out of three pairs, two are opposite. Therefore, it is said to be the trans. The question is, these two are the geometrical isomers. How many optical isomers are possible? Let us see. Is it optically active? Say yes or no. No, it cannot bisect into two equal half mirror images. It is not possible. It is not having a planar symmetry. Just now I have shown. AB will be above the plane, another AB will be below the plane. They are in the different plane. So you cannot divide into two equal halves. There is no planar symmetry for cis compound. Same manner, there is no planar symmetry for trans compound. Therefore, both are optical active compounds. This compound shows two optical isomers D and L. This compound also shows two optical isomers D and L. Therefore, total number of optical isomers are 4. Both are optical active compounds. Now let us take the third example, MA2B2. Two are bidentate ligands, two are normal monodentate ligands I have taken. A is a bidentate ligand, B is a monodentate ligand. Two are bidentate ligands, two are monodentate ligand I have taken. So with this combination, possibilities are I can write AA and BB. Is one possibility. Second one, keeping the first one constant, AB and AB. Two possibilities are there. Therefore, number of geometrical isomers are 2. Here I have represented the geometrical isomers. Look at here, B and B exactly opposite. This the bond angle is 180. Therefore, I represented the trans compound. In similar type of ligands, if the bond angle is 180, the compound is said to be trans compound. And here AA and AA is there. So therefore, this is a trans compound. In trans compound, it is optically inactive because I can bisect into two equal halves by taking this plane. This is a plane where I can bisect to two equal halves. That's why it is optically inactive. It is having a planar symmetry, therefore it is said to be optically inactive compound. I'll repeat once again. Third example, similar monodentate. So bidentate ligands are two. Two monodentate ligands are also identical. Two geometrical isomers are possible. One is trans, second one is cis. See, B and B are identical. Angle is only 90. So therefore it is cis position. Here also remaining two are cis position. This is trans, this one is cis. And now this compound is not having a planar symmetry. One is above, second one is below. I cannot bisect into two equal halves. Already I have shown. Now, this compound is not having a planar symmetry. If it is not having a planar symmetry, the compound is said to be optical active compound. Now, it has its mirror image that will be non-superimposed mirror images. Therefore, this compound is optically active compound. If it is an optical active compound, two optical isomers are possible. One is D, second one is L compound. So therefore, number of geometrical isomers are 2. Number of optical isomers are 2. Total number of stereo isomers are 3. So that's about third example. Now we'll go for the fourth example. Two are identical bidentate ligands and two are different monodentate ligands are taken. Now, with this combination, two possibilities are there. This is trans compound and this compound is said to be the cis. So here, these two are adjacent positions, but these two are exactly opposite. With respect to B and C, I said it's a trans compound. Here B and C is adjacent, 90 degrees, therefore it is a cis compound. In the previous case, trans compound is optically inactive because of planar symmetry. Here also same thing. This is a plane. I can divide this molecule into two equal mirror images. Therefore, it is having a planar symmetry. If it is having a planar symmetry, the compound is said to be optically inactive compounds. Normally, trans compounds in general are optically inactive due to the planar symmetry. Two examples I have given. Now look at the other one. Cis compound. In cis compound, there is no planar symmetry. Just an organ. This is above, this is below. They cannot be in one plane. This molecule is not having a planar symmetry. Planar symmetry, if it is absent, the compound is optically active compound. Cis compound is optically active. Proof is I have given its mirror image. These two are mirror images, but non-superimposed mirror images. Such pair is said to be optically active compound. Therefore, one is D compound, second one is L compound. Geometrical isomers are 2, optical isomers are 2, but stereo isomers are 3. This is the fourth example. We'll go for the fifth one. See the fifth example. M, AA, B2 and C2. AA is the bidentate ligand, one bidentate ligand. Two are monodentate ligands of one category, two are monodentate ligands of other category, right? This is the fifth example. Now with this, two possibilities are given. AA, BB, CC, one possibility. Second possibility is AA, BC, interchange of these two. So therefore two combinations are possible. That clearly indicates this molecular formula can have only two geometrical isomers. What are those two geometrical isomers here are given? This is trans compound, this is cis. Why this is trans? Similar substituents are exactly opposite. Bond angle is 180, therefore this compound is said to be the trans compound. Now, similar substituents are adjacent. Look at here, this is 90, this is also 90, this is also 90. Therefore, this compound is said to be cis compound. Now, look at trans compound. Trans compound is optically inactive. Why optically inactive? Look at carefully this one. This molecule can be divided into two equal half mirror images. Therefore, I can bisect this molecule into two equal halves. Either this way or this way. You can see here also planar symmetry is there. So this molecule is having a planar symmetry. So therefore, due to the planar symmetry, trans compound is optically inactive compound. You can cut this molecule into two equal halves. This is a planar symmetry, therefore optically inactive compound. But whereas here, cis compound is not having a planar symmetry. You cannot divide it into two equal halves. Now it has its mirror image. These mirror images are non-superimposable. Any compound is having a non-superimposable mirror image. Imageability will be an optical active compound. Therefore, cis compound is optical active compound and trans compound is optically inactive. Third example I have given, all trans compounds are in general optical inactive compound because of the planar symmetry. But whereas in case of cis compound, there is no planar symmetry, therefore they are optically active compounds. Here, if it is an optical active compound, one compound rotates plane polarized towards right side, another one rotates towards left side. Therefore, this compound is optically active and dextro and LIGO compounds are there. So these are the few important examples of bidentate ligands with geometrical and optical isomerism. So next class will continue for another video. Thank you. అది ఎంత వీడియో ఎంత అప్లోడ్